Hello, and welcome to my report on Lab 5. In this lab, we were asked to perform a simple experiment dropping a bar magnet through a tube of aluminum foil. We then had to analyse the video footage to find out the exact amount of time taken for the magnet to drop through the tube. Next, we had to create the computational model for the experiment, and lastly, compare the findings in the experiment to the output of the model. The first thing we needed to do was run the experiment. In order to do this correctly, we needed to know which side of the magnet was north and which was south. This is because later, in the model, we'll reproduce the experiment with the North Pole facing up. In order to have our data match this, we need to mark north on the bar magnet using the magnometer from Lab 3, and make sure we dropped it with the north pointing up each time. Here you can see the setup which I used. There is a stopwatch in the background so that when scrubbing through the footage, I know exactly how much time elapsed between the magnet entering and exiting the tube. You can also see the data which I recorded. I didn't restart the clock each time, so the starting times are all different, but by taking the difference of the start and end time and averaging them, I found the time taken for the magnet to fall through the tube to be 1.052 seconds. This value I think will be quite low compared to others because I struggled to find a roll of foil which had a sufficiently large radius. The instructions asked for the foil to be 1 centimeter thick, but as we'll see in a moment, this brand new roll of foil was only 3 millimeters thick. Having completed the experiment, the next step was to create a program to model the output. The first step here was to input the initial conditions into the code. The foil's tube length was 30 centimeters, and as we just discussed, the foil on the tube was only 3 millimeters thick. The inner radius of the tube was 1.3 centimeters. For the magnet, I measured the mass to be 98 grams, and from Lab 3, the magnetic dipole moment was 3.2 joules per Tesla. This is another point which I think may cause an issue in the model, as I remember this value being potentially inaccurate. After copying my function for the magnetic field of the bar magnet from Lab 3, I worked on the function to calculate the magnetic flux. As you can see on this slide, we're trying to calculate this equation in code. We set the variables for ring radius, distance and speed, and then calculate the numerator and denominator as per the equation for the magnitude of change in flux over time. We then had to calculate the ring's current, which Faraday's law tells us is equal to the negative change in flux over time divided by the resistance. We'll then use that value in the next section, here where we use Newton's third law to calculate the force exerted on the magnet by the whole tube, by calculating the force on each ring due to the magnet. For each ring, we get the magnetic field from our Lab 3 function, then we calculate the unit vector for the B field. Sine theta is equal to the magnitude of the cross product of mu hat and B hat, which we use to produce the output for the equation for the force on loop. By Newton's third law, we know that this is the same as the force on the magnet, and add it to the total force. We then set the net force to be equal to the sum of the force due to gravity and the force due to the tube on the magnet. Using this, we use Newton's second law to update the bar's velocity and position, as we know from previous physics classes. Here, we use the final velocity is equal to the initial velocity summed with the product of acceleration and change in time, and the final position is equal to the initial position summed with the product of final velocity and change in time. Here you can see the output of the model, and it supports our expectation as we see the magnet accelerate until it reaches the tube, where it falls with a constant speed. The difference between the experimental and calculated time to fall is quite a lot, but I've already covered a couple of reasons why that might be. Namely that the tube didn't have very much foil on it, and that the value for the magnetic dipole from Lab 3 might not be quite right. Lastly, we have the final questions, the first of which asks, what would happen if the resistance of the loop became close to zero? This would increase the current to near infinity, which would make the force on the magnet near infinity also, so we would see the magnet get pushed out the top of the tube. The second question asks what would happen if holes were cut in the tube. I imagine this would increase the resistance of the conductor, which would lower the force on the magnet, making it fall less slow. This concludes my report on Lab 5. Thank you very much for listening.